Okay, welcome to lecture 5 of the Transducers course. As usual, let us recollect what we have learned so far. We looked at the static characteristics of transducers. The static characteristics, as the name name indicates, is the character of the transducer for uh, input that doesn't change with respect to time. Or as electrical engineers, we can say it's a DC characteristics, where my input is DC and I look at my output, right? In the static characteristics, we talked about the resolution, the full scale, the sensitivity, the overload factor, accuracy, and precision. Even in the static characteristics, uh, the dynamic uh, play a part. But even if I have a constant input, at some point I am going to apply that input to my transducer. So I have what is known as a step input, right? DC also comes into the fact because at some time I will just switch it on, right? So when I switch it on, it goes from so if this is my input X, right, we call this signal X into U of uh, X into what is happening, it's not erasing. Technology is really bad. Okay, uh, X into U of t, where U of t is known as the unit step function. T equal to 0, it goes to 1 and stays as 1, right? uh, U of t I am not getting right. Oh, this is the okay. U of t equal to 0 for t less than 0 equal to 1, t greater than or equal to 0, right? So that's the unit step function. We already know this from our uh, undergraduate studies. Okay, so if we do that, if this is my input, then it's possible that my output will go like this, right? And of course, it need not be like this. I can also have my output. We will look at this a little later, right? This is also possible. This is for one system. This is system or transducer, right? Uh, Transducer 2. This is transducer. So we get the final output settling to what we expect, and we also learned that it is transient state or transient period, and this is steady state, right? The time taken for a transducer to attain steady state and um, give correct output is known as the response time, also known as settling time, right? Uh, so this can vary sometimes uh, tens of seconds to few seconds to few milliseconds to few microseconds, depending upon the type of transducer. that we use. This is dynamic characteristics, but for a static input, right? Then what happens if my input itself is dynamic? Input is dynamic. What do you mean by dynamic? I have x of t, right? My input varies with respect to time. In this we saw that x of t, when it becomes a time varying quantity, can be aperiodic or periodic, right? Periodic means repeats every cycle, right? There is one cycle of change and that cycle keeps repeating again and again and again. Now whether aperiodic or periodic, we, unless otherwise we know what is the input, we cannot define the output of a transducer. But that is not really an option that we can live with, because we should know what is the what kind of characteristics that I am going to get. So what do? We now say that I will look at the dynamic characteristics of a transducer for standard repetitive signal. Right? For reasons similar to the circuit theory, this standard repetitive signal is the sine or cosine function. Right? We can use either sine or cosine. If you look at books that are old, they would have used sine omega t as the standard function. Most modern books use cos omega t, because cos omega t has certain characteristics. We can define cos omega t as real part of e power j omega t, and thus it has become a standard. In fact, IEEE, which is the nodal authority on anything and everything that is electrical, now says cosine is the standard function. It doesn't matter what is the big deal between sine and cosine. There is only 90-degree phase shift between them, right? So what we do is we give the input as a sine function. Let's say root 2 x cos 2 pi f t, right, as the input. It could be temperature, it could be pressure, it doesn't matter, whatever is the input, and then we find out y, right? And in 99.9% of the cases, our transducer is going to be a linear device, right? Which means the rules of linearity apply, cumulative law and associative law. Then y can be in general root 2y cos 2 pi ft plus phi, right? It has to be the same frequency because it's linear system, and linear system can allow certain phase shift in the output. That's the only thing. So this, we call this as the amplitude. This is the phase. Of course, this is the frequency. We already saw in the last class, frequency is measured in terms of cycles per second, which is hertz, and 2 pi f is omega, which is radians per second, right? So we now vary f, right, and find out what is the input output characteristics of a transducer. So I vary f and I get the input output characteristics of a transducer. We call this as frequency response characteristics, right? Because this is amplitude. It could be output amplitude by input amplitude, or simply keep the input amplitude constant and find out what happens to the output amplitude. Now we already said that we will have to put a particular cutoff frequency Fc. We call the frequencies that are less than Fc is pass band, and above is called stop band, right? This again we have learnt in our earlier undergraduate courses, right? So this we call it as a low pass filter characteristics. Low pass filter, or simply LPF. The Fc is determined at which power at Fc is half the power, I'll call this as expected power, half PE, right? So the band of frequency is called bandwidth. We also call this as half power bandwidth, right? Sometimes, especially when we are dealing with low power, right, we also express power in a unit called decibel, right? This is decibel, right? dB. Uh, what is decibel? Deci means 10. So power in dB is 10 times log P naught by Pi. Of course, in this case, for our transducer, it will be 10 log P naught by P expected, right? So we see that it's in the logarithmic scale. So it's one way of extending the range without sacrificing the kind of understanding that we can get from the characteristics, right? Uh, but if I assume that the amplitude, output amplitude is in volts, right? Say I am getting a output of a transducer as a voltage output, then I know power is proportional to V naught square, right? The output, let me not use V naught because here in this course we use V for velocity, so I will use EMF. So output E naught square, right? If I use RMS value as E naught, it will be E naught square. Anyway, it doesn't matter. We know it is E naught square. So if I now put in terms of the dB, dB is 10 log E naught square by EI square, which is also equal to 10 log, for our case, E naught square by E expected square, right? So if I now take this, this is 10 log, that is equal to 10 log E naught by E expected whole square, and log of A square is 2 log A, so 20 log E naught by E expected. That's the power level. If power level is half, if P naught by P expected is equal to half E naught by E expected square is half, so that leads E naught by E expected is equal to 1 by root 2, right? Because this is, that leads to E naught equal to 1 by root 2, or E naught is equal to E expected by root 2, which is 0.707 times E expected. So if I now look at the characteristics, let's say this is my output characteristics E naught, where E input is constant, I'm not changing the input, magnitude of the input amplitude is constant, right? With that, if I look at the frequency, I have Fc, so this would be 0.707 times E expected, right? Okay, E expected. So this is E expected. In most systems, we use this half power bandwidth whenever we talk about bandwidth of a system. But when I talk about a transducer, I am at cutoff frequency Fc. At Fc, I am going to get 0.707 times the expected magnitude. What does it mean? I am trying to get EE, right? Whereas what I am going to get is 0.707. So if I look at this, this is 0.707 EE minus EE by EE into 100 will be the percentage error in my measurement if I measure it at the particular frequency, right? That the at exactly the cutoff, right? And so the 0.707 this would require 29.3% error. This is minus 29.3% error. And of course, we don't want such large errors in our transducers. So when it comes to transducer, the half power bandwidth, sometimes we also call this as minus 3 dB bandwidth, right? So when I have half power, this is 10 log P naught by Pi is half, right? This is minus 3.010 dB, right? So half power also means minus 3 dB in terms of measurement at using the decibel as a unit. So either we can call this as the half power bandwidth or 3 dB bandwidth. We normally don't say minus 3 dB. We simply say 3 dB bandwidth. Whatever it is not good for a transducer because the error is almost 30%, right? So what do we do instead? We do not specify bandwidth of the transducer. This is very, very important. Bandwidth of a transducer is not specified, or even if it is specified, it's useless, as half power minus 3 dB level, right? Most of the time we put the bandwidth as 0.5 dB or sometimes even minus 0.5 dB or minus 0.1 dB level, right? So at minus 0.5 dB, the error would be about 6%, and the minus 0.1 dB, the error would be about 1%. This is approximately 5.6% error. This is approximately 1.1% error. So please note that when it comes to bandwidth of a transducer, most of the time we do not rely on the half power or minus 3 dB bandwidth because that's useless. At that point, my error is really 30%. I cannot use that for measurement. So when it comes to transducers, we use half a dB bandwidth or 0.1 dB bandwidth, so that the errors are within minimal. So if we look at another right important characteristics in the dynamic characteristics is the bandwidth, right? So the and we also know that there are four possible characteristics: the low pass filter, the high pass filter, the band pass filter, right, and the band reject filter or notch filter. This is frequency, this is amplitude, right? So this is low pass filter characteristics, this is high pass filter characteristics, this is band pass filter characteristics, this is notch filter or band reject filter, right? The now this is fine. I know I have the input output characteristics for a dynamic input where I have a time changing input. I get the frequency characteristic, frequency response characteristics of the transducer. But how will that help me in real world? Because the real world, as I said, my input could be something like this, or input could be repetitive, but it is not a nice sine wave, right? Something like this. But we know that I can use Fourier series and expand. If this is my input x of t, x of t is equal to a naught plus sigma n to n is equal to 1 to infinity a n cos n omega t plus b n sin n omega t, right? So I can now split my input into series of sinusoids and then find out for each sinusoid what would be my transducer output, add again, and I will get the response for this, right? Of course, if it is aperiodic, I can use Fourier transform and get the frequency response characteristic, something like that. This is frequency, this is amplitude, right? So the advantage of getting a characteristics of a transducer in terms of sine wave signal whose frequency is varied from one level to the other, right? One value to the other, right? Normally 0 to whatever high frequency that we want, we can change and get the frequency response character of the transducer. If I want the characteristics for any particular type of input, all I have to do is resolve my input, time varying input, in terms of sines and cosines, and then because I already have a frequency response characteristics, I can predict what would happen to my output, whether my output is going to faithfully reproduce the input or there is going to be some change, right? And the the output is going to be right. The output is going to exactly represent my input. Many times we may not sometimes really bother about this because it can be that I really do not expect my output to be faithful reduction of the input. I can allow certain right uh, the output can be uh, missing some part of the input in that sense, right? And we can live with that. It's not a big problem, right? Okay. Now, apart from the sine signal, there is another form of signal which is known as the impulse signal, right? Uh, why did we use the sine signal? We said we wanted some standard signal which I can use it for representing my input, right? But it so happens that we chose sine omega t as the standard signal. It's also possible to use another signal called the impulse function. This is given by a famous mathematician called Dirac. So we also call it as Dirac delta function, right? So before going to impulse, let us look at what is a pulse. Pulse is in with respect to time, I have the input uh, available to me in terms of uh, certain period, certain amplitude, right? So this is amplitude, this is period. Let me say this is minus tau by 2, this is plus tau by 2. So width is minus tau by 2 to plus tau by 2. So this width, pulse width is tau. Let me say that it can be any amplitude signal. I am taking the peak amplitude as 1 by tau, where tau is the pulse width and 1 by tau is the amplitude. Now if I put a limit on tau, let me call this as pulse p of t, right? That would give me the impulse del of t, right? So what happens when I reach tau equal to 0? Please remember amplitude is 1 by tau. So amplitude becomes 1 by 0, so which is infinity, right? And width is 0, right? Because the pulse width tau becomes 0. So this is narrow width, but amplitude is infinity. Of course, it doesn't make sense. Infinity itself is a problematic number in mathematics to deal with, but as a kind of a signal, this is really very nice to handle. And if I use this signal and use mathematics, we get quite a lot of information about any system. Forget about transducer, the impulse characteristics of any system gives us a lot of insight into the system behavior, right? So if my input is del of t and I find out what is the output, right? Input is del of t, then output I get is called impulse response, right? The uh, the problem, this is mathematically perfect, but this what happens? See, for example, uh, I have 2 del of t. Right? Let's say 2 into del of t. What happens? It's already going to infinity, right? So how do we handle this? Now let's look at how I can get 2 del of t, right? The 2 del of t, I have the same pulse, right? This is minus tau by 2, this is plus tau by 2, this is time, this is amplitude, and this is 2 by tau, right? So this is limit, I call this as 2 into p of t, twice the amplitude of the pulse, right? T tending to 0, tau tending to 0, uh, 2 into p of t, right? So that is equal to 2 into del of t. So if I look at the difference between this, if I look at the energy in the pulse here, this is 1 by tau, width is tau, so it is 1. If I look at the same energy here, the magnitude is 2 by tau, width is 1 by tau, so it is 2, right? Or the area under the curve is 1, right? So one way of and putting it is minus infinity to plus infinity del of t equal to 1, right? If I find out the area under the curve, it has to be 1. And what is do del of t? Integral minus infinity to plus infinity 2 into del of t, of course, is 2, right? So uh, in terms of definition, which is strictly not correct, but I can say del of t. I repeat once again, this is really not mathematically correct, but many times we do this approximation. I can say del of t equal to infinity at t equal to 0 is equal to 0 uh, when t is not equal to 0, and integral minus infinity to plus infinity del of t equal to 1. So this is one way of telling the definition of del of t, right? So we can define the impulse function, right? And when we get uh, the output for an impulse function, we can find out for any x of t by simply using the impulse response characteristics. The impulse response characteristics is also very nice in the sense, if I take the Fourier transform of del of t, which is 1. What does it mean? What does Fourier transform gives us? It is giving us in the frequency domain the magnitude. So when I say frequency response is 1, what we really understand is that the impulse del of t contains all frequency. In fact, it goes from minus infinity to plus infinity, all frequencies with magnitude 1. So if I give an impulse to my transducer, what I am actually doing is I am exciting the transducer with uh, with all frequencies at the same instance, and I am getting the output. So which means instead of frequency response characteristics where I keep varying my sine omega t, the omega of sine omega t from whatever range I want, 0 to 500 radians per second or something like that, when I give an impulse, I actually am varying the frequency from minus infinity to plus infinity and finding out the characteristics of the transducer. So impulse response characteristics is another uh, nice way of defining the dynamic characteristics of a transducer. We will come back a little later to our impulse response characteristics. Now, if I look at my transducer as a black box, I have an input which could be temperature, pressure, displacement, anything. I have an output, right? So I can uh, model this as a simple system, right? Input output system. Transducer is a system, okay? So the advantage of treating a transducer this way is that the modeling of a system is a very mature uh, uh, area where a lot of work, both in terms of mathematics and in terms of practical applications, have been done, right? Let's look at the transducer. There is a physical part, I call this as mechanical part of the transducer, and there is an electrical part of the transducer, right? So if I look at any transducer from the mechanical part, it may have a mass, it may have viscous or elastic damping, viscous damping or uh, frictional damping. Sorry, just 1 second, let me take a swig of water. Right, and it can also has a compliance, or what we call it as stiffness or elasticity. We also call this a spring, right? Elastic spring. Okay, so I can simply put a block diagram. Uh, this is mass M suspended by a spring. I call this as Ks, and a damp. This could be viscous damp or damping or frictional damping, it doesn't matter, D, right? So I can now look at, I apply a force, this can be a force or anything like that. Then the if I say this is my reference signal, uh, the mass would move by x, right? The mass would move by x, right? So if I look at the force when I give to the system like this, some part of the force goes to into the mass and moves it by x. Some get stored in the spring, some may get dissipated in the damper, right? If I add all this, I should get the force. So I can now write the model of the system as mass into acceleration, d square x by dt square, right? Plus viscous damping or frictional damping into velocity, dx by dt, plus ks into x will be the force, right? Now this is a second order differential equation that describes a mechanical system. Uh, Now if I look at the transducer, it has a mechanical part, right? Uh, and it has an electrical part, right? So I can model the mechanical part, as I said, as a mass spring and accelerometer, mass spring and damper. Electrical part, I can model it as R. Let me put this in a different perspective. LRC, right? So I call this as LM, RM, and CM, right? Now, if I look at the current I in the circuit, the EMF will be Lm into di by dt. This would be I into R M. This would be 1 by Cm into integral I dt, right? That will be the voltage here. So the total voltage E, I can write it as E equal to L di by Lm di by dt plus dm Rm or m into I plus 1 by Cm into integral I dt, right? That would be the total EMF E across the circuit. Now I also know I is equal to dq by dt, right? So substituting here, I get Lm d square q by dt square plus Rm into dq by dt plus I by Cm, because q by Cm is equal to E, right? So now I look at this equation with respect to this equation. These two, mathematically they are identical, right? It's a second order differential equation. Only the coefficients and the variables are different. Here I get to multiply by Lm. Here I get to multiply by the mass. Here I multiply by the resistance in the circuit. I multiply by damping constant. Here I divide by Cm, I multiply by the spring constant. On the right side, it's mechanical force. This is electromotive force, EMF, right? So now I can say the mechanical system is equivalent to the electrical system when it comes to the representing the system as a set of differential equations. So we call this as direct mechanical to electrical equivalence, right? So here I know displacement x is charge q, right? Mass is inductance L, R is damping constant D, uh, spring constant Ks is 1 by Cm. Sorry, this side it should be damping is Rm, inductance Lm, 1 by Cm. So if I really want to analyze a transducer, I can now replace my mechanical part. With this we will do when we really look at the frequency response characteristics, other characteristics of transducers that we are going to learn. And the advantage is that the moment I put this equivalent circuit, I immediately get everything in the electrical side. I don't have to worry about my mechanical side. I can analyze the transducer as though it is a completely electrical circuit. This will become much more clearer when we actually learn about transducers and how we are going to model each transducer to understand how the transducer will behave for different kinds of inputs. Okay, so The one thing is, if I have a mechanical system with mass, spring and damping, and I have an electrical system with inductor, resistor and capacitor, uh, these two can be equated through the differential equation. Of course, in this case, I have used a series LRC circuit, right? I can also put a parallel LRC circuit, right? Inductance, resistance and capacitance, right? I have EMF E, so I have current I flowing in the circuit. This is IL, this is IR. I'll have to make it look like a resistor, right? And this is IC. So this is C R L. Now, what is the equation? So I have I is equal to IC plus IR plus IL, right? The current entering in the circuit. Now let me see what is IC. There is a voltage EC, right? So IC is C, right? What is the voltage? Uh, right? So this is E by R. I can immediately write this, right? Voltage, this is L DIL by dt 1 by C right, into C dV by dt. So sorry, this is not 1 by C. This is C equal to C into dE by dt plus E by R plus L. Sorry, this is not correct. L di by dt is the EMF. So I need to get to the EMF, right, in terms of IL. So this will be 1 by L integral E dt, right? Now I know the in terms of um, flux, I can generate an induced EMF E equal to d phi by dt, right? Of course, minus n d phi by dt. Let's not worry about the n and all that. So now I can write this as C d square phi by dt square plus 1 by R into d phi by dt plus phi by L equal to E, right? Equal to I, sorry, right? See, IC is this, IR is this, IL is this, so this must be total current I. Now I will rewrite the mechanical equation. M d square x by dt square plus d dx by dt plus ks into x equal to force. Now if I look at these two equations, they are also similar, right? It's a second order differential equation, right? But we see now the x, the displacement becomes flux phi, and mass becomes capacitance, 1 by R becomes damping ratio, and or conductance, right, becomes, and 1 by L is Ks. So this is known as inverse equivalence. A mechanical system can be considered as an equivalent electrical circuit. If we use the LRC circuit in series, we get one set of equivalents where mass becomes inductance, resistance becomes damping constant, and 1 by capacitance becomes the spring constant. On the other hand, I can also put an equivalent which is the parallel LRC circuit. In that case, the displacement becomes flux, force becomes current, right, and so on. So it's possible to use uh, either the direct equivalence in terms of mechanical to electrical modeling, or the inverse equivalent also can be used to represent mechanical. So I stop here. We will continue in the next class.